Electromagnetism is the study of the relationship between electricity and magnetism. The idea came about when a Scottish physicist named James Maxwell proposed the idea that light is actually the interaction of electric and magnetic fields. Really, what Maxwell did was show that all magnetic and electric phenomena can be described using only 4 equations that related to electric and magnetic fields. These 4 equations, now known as Maxwell's equations, are considered the fundamental equations for all electromagnetism in the same way that Newton's laws of motion are fundamental for mechanics. Even better, while Newton's laws conflict with the theory of relativity, Maxwell's equations are consistent with the theory of relativity. The math involved with Maxwell's equations is nothing to sneeze at and really beyond the scope of this course. So we will just summarize each equation and how we can use it to describe electromagnetism. The first equation is a generalized form of Coulomb's law and basically dictates how an electric field behaves around electric charges. Remember that electric fields originate on positive charges and end on negative charges. In this regard, we can think of a positive charge as a source for electric field. In turn, then, a negative charge is sort of like a sink for electric field. It also defines the electric field as the force per unit charge acting on a test charge. The strength of this force is related to the permittivity of free space. This is Gauss's law of electricity, and it tells us that the electric charge of any shape produces an electric field. The second of Maxwell's equations comes from Gauss's law of magnetism, which says that the divergence of electric flux depends on the electric charge density. This is similar to the first law, except that magnetic field lines are always continuous. So the magnetic flux moving inward towards the South Pole will equal the flux moving outward from the North Pole. This means that the net flux will always be 0 for a dipole source. Since it is impossible for a magnet not to have 2 poles, this is always true. Really, if we do the math with this equation, it actually proves that a magnetic monopole cannot exist. Maxwell's third equation is really just a combination of Faraday's law with Lenz's law. We know that changing a magnetic field induces an electromotive force, which in turn induces the electric field. The final equation is Ampere's law, which says that a magnetic field is produced by a current. The second part, about how magnetic fields can be produced by changing electric fields, was a hypothesis put forth by Maxwell based on the idea that there is a lot of symmetry in nature. So if Faraday's law regarding the creation of electric fields from magnetic fields was true, then the opposite must be true as well. Based on these 4 equations, Maxwell proposed that a magnetic field will be produced in empty space if there's a changing electric field. It becomes interesting when we realize that if a changing magnetic field produces an electric field, then the electric field will be changing. And a changing electric field produces a magnetic field, which will be changing and producing a new electric field. That will be changing, and so on, if you get the idea here. So basically, one will propagate the other in one long continuous pattern. Now, at Maxwell's time, it was well known that light would behave like a wave, but no one had been able to determine what type of wave it was. So Maxwell proposed that it was, in fact, an electromagnetic wave. We can represent an electromagnetic wave by drawing its electric and magnetic fields. In this diagram, the blue represents the electric field, and it is moving along the y-axis. The red represents the magnetic field moving along the z-axis. The entire wave is moving along the x-axis. So the electric field is moving in a plane perpendicular to the magnetic field. We can use our right-hand rule to determine the direction of the velocity vector. If you align your fingers to the electric field and curl them in the direction of the magnetic field, your thumb will point in the direction of the velocity, which we know turns out to be perpendicular to both the electric field and the magnetic field. So we know the direction of the velocity. But how fast are those waves really going? If you decide to move forward a few courses in your study of mathematics, what you will notice is that Maxwell's 4th equation is actually a wave equation. Recognize these constants? Those were the constants that were already in use for calculating the strength and direction of electric and magnetic fields. These constants were needed in order for the existing equations to correctly determine the values. But it turns out that when Maxwell grouped these 2 constants together, he was able to determine the speed of the electromagnetic waves. The velocity of an electromagnetic wave is given the designation of lowercase c. And after a lot of math, Maxwell determined that the speed of an electromagnetic wave boiled down to the ratio of the strength of the electric field to the strength of the magnetic field. A little bit more math, and we can write this expression in terms of the electric and magnetic field constants. If we plug those constants in, we can solve for the speed of light, and we find it to be right at 3.00 times 10 to the 8th meters per second. Now notice that we have left out a lot of how these equations were derived. If you're really interested in the actual math, you can Google Maxwell's equation and find lots of places that will walk you through it.